Welcome everyone, this is Math 103, Unit 2, Section 9.1 on sets. Sets are collections of things. It could be a set of steak knives, a set of golf clubs, but in math we're talking about sets of numbers. And we're going to learn several different ways of writing these sets. And this will be important because when we solve inequalities, we're going to get answers that aren't just a single number, it's whole ranges of numbers. So we're going to need ways to write that. First way is going to be the roster method. The roster method is like a roster of a football team where you just list all the members. And we're going to have a description of words that describes a set, and then we'll write it. So we're going to use the roster method to write the set of negative integers that are greater than -4. So let's break this down. First of all, the integers. Integers are the whole numbers, but they're both the positive and the negative versions. So you get all the negative numbers, all the positive numbers, and 0. And we want just the negative integers. And negative integers that are greater than -4. Now when it says greater than, it means strictly greater than. So that means we're going to start at -3 and go to -1. So when we write these, start with a curly brace. This indicates that we're starting a set. Traditionally, the smallest number is written first if you have a sequence of numbers. So when you go from -3 to -1, and that's all the negative integers that are greater than -4. Because when we get to 0, that's no longer a negative integer. So we're going to stop at -1. And just make sure your list is separated by commas. It's called a comma-separated list. Your turn number 1. Use the roster method to write all the positive integers that are less than 5. Now just a reminder, I don't stop during the video, so pause the video, work on the your turns, and then restart. So we're going to start with a curly brace. Now we want all the positive integers that are less than 5. So positive integers start at 1. So go 1, 2, 3, 4. And less than 5 means strictly less than 5, so not including 5. So that set will be 1, 2, 3, and 4. Now we're going to use the roster method to write the set of positive integers that are greater than or equal to 6. So we're starting at 6. And then we're going to go up from there, and this list goes on forever. Now clearly we can't write all the numbers that are greater than 6. So we're going to use an abbreviation. We're going to use ellipses. So all the positive integers greater than or equal to 6, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on forever. So we're starting at 6, since it's greater than or equal to. Greater than or equal to means we're going to start right at 6. Now what we're going to do is establish a pattern. 6, 7, 8. We know we're just counting up from 6. And we don't want to list them all, so here, just include 3 dots, and these are called ellipses. So we establish a pattern going up by 1, and generally 3 numbers are used to establish the pattern, and then the ellipses mean that the pattern continues. So 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. Now your turn number 2. Use the roster method to write the set of negative integers that are less than or equal to -3. Now in this case, we're not going to start with the smallest number because we need to establish the pattern. So we're going to start with -3 because it's less than or equal to -3, and we want all numbers less than that. So -3, -4, -5, comma, and ellipses. Some people may want to write it in the more traditional method, ellipses, and then, let's see, -5, -4, -3, and then stop. If you want to do it like the number line where you got the smaller numbers to the left, then you can write it like that. Either one of those is fine. Now there are 2 mathematical operations that can be done with sets. And These work by taking two sets and combining them into a new set. And the first way to do that is by finding the intersection. So the intersection is like the intersection of some streets. It's where things come together, and we're talking about the parts where the two streets have in common. So we go one street coming this way and one street coming this way. The blacktop that belongs to both streets is there in the middle, and that would be what's commonly known as an intersection. So read through about Rhonda and her sock drawer, and this will help give you an intuitive idea for what an intersection is when we talk about numbers. All right, so Rhonda has some single socks in her drawer, black, tan, green, aqua, blue, and gray. And then in her laundry basket, she's got red, brown, green, white, purple, black, yellow, and blue. So what we want to do is we want to create matching pairs of socks. And with these two lists of socks, the matching colors, there are 3 of them, are green, black, and blue. So there's our 3 matches. So think of the intersection as being the matches. That's what we're looking for. So in general, the intersection of 2 sets, and the symbol for intersection is an upside down U. So let's say we have 2 sets A and B. If you want to find the intersection, you write it A, intersect, B. That's the symbol for intersection. And this is all members of A and B that are in common between the 2 sets. All those matching elements. So find the matching elements in your turn number 3. We're going to find the intersection of those 2 sets. So A is even numbers up to 10, and B is 1 through 5. Now the matching elements in these 2 sets, all right, we've got 2 here and 2 here, those match, and then 4 here and 4 here. So we have 2 matching elements. So write the intersection, A intersect B. All right, set notation, and then roster method, write out those 2 elements. So the intersection of set A and B are 2 and 4. Now for B, we've got a different set here. We've got A is 2, 4, 6, 8, 10, but B (1, 3, 5, 7, 9). Now if we look at A and B, we have no elements in common. So the intersection is empty. There are no elements in the intersection. And we have a special symbol for that. That's called the empty set. It's a 0 with a line through it. And that means the intersection of A and B is empty. There are no elements in common between A and B. Let's turn to the next page and read about the union of sets. The Ogevik Ski Emporium has 2 locations in Ironwood and Houghton. So if someone calls and wants to see what kind of skis are available, we're going to list off the different brands. And we don't want to limit it to one location. We want to list all the brands available at either location. And that's what the union is. It's any element that's in either of 2 sets. It doesn't have to be in both of them. It just has to be in one. As long as the skis are available at one of the locations, we can tell the customer that they're available. So if the keyword for intersections is match, a keyword for unions might be either. Anything in either place. And there are 7 different brands. All right, we've got Nordica, Solomon, Armada, Rosenal, Head, K2, and Atomic. Those are 7 different brands available at the 2 locations. And that is the union then between Ironwood and Houghton. And we write the union as a big U, so it's easy to remember. So Ironwood, Union, Houghton. There's the symbol for union. Remember, intersection is going to be the upside down U, and then U for union. So in general, the union of 2 sets in a more formal way is X is in set A or X is in set B. So or is the key word here. Here the key word is and. But for unions, it's or. It's either in Houghton or in Ironwood. It's either in set A or is in set B. All right, let's apply this to your turn number 4. We're going to find the union between A and B, where A is 3, 4, 5, 6, and B is 2, 3, 4, 5. Now we're not looking for matches in this case, we're looking for any number in either one of them. So A union B. Union is like bringing things together. So we got a 2, a 3, a 4, a 5, and then we also have a 6. Doesn't matter if they're listed in each set, we just write them once. Don't need to write anything twice. So the union of A and B is going to be 2, 3, 4, 5, 6. Now for B, got A is the evens and B is the odds. And between the two, we have every number between 1 and 10. So the union is all numbers between 1 and 10. So I'm going to write it using some ellipses, establish the pattern 1, 2, 3, continues on, and finish off 8, 9, 10. So it saves a little bit of writing that way. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the union of A and B. Now I've got a little set vocabulary and some symbols. Set notation, as we've seen, it's the curly braces, and we'll see that in both roster notation and in set builder. Then we've got an element, and if you write kind of a funny looking E, that's the symbol for element, and that just means something is in a set. So 2 might be in set A, so 2 is an element of A. It's also known as a member of A or an element of A. And the last is the empty set, as we saw, is 0 with a line through it. That'll be an important one because that might be the solution to an equation. If there's no solution, right, it's the empty set. Empty set meaning there's no solutions. Now set builder notation has a certain format, and this is one way we're going to write sets of numbers, and one way we're going to write the solution sets to equations. So set builder starts with a curly brace, and next goes the variable name. Whatever letter you're using, could be X, could be A, whatever variable, doesn't matter. And then we write the vertical line. And this is read as such that. So we state the variable x, such that, and then over here are going to be the requirements for x. Usually some restrictions. Usually we don't want every real number. We want to restrict it down to certain numbers. And in this case, we'll be signifying that with a inequality. So for the first example, if I want to write all real numbers less than or equal to 5 using Set Builder, first I'm going to just make up a variable. Could be x, could be some other letter. It doesn't matter what letter you choose. All right, then the vertical line, so x such that, and then I'm going to say what my restrictions on x are. So x has to be less than or equal to 5. So x is less than or equal to 5. All right, so there's our restrictions. We don't want all the numbers greater than 5. We just want the ones less than or equal to 5. And then close it off with some curly braces, and there's Set Builder. So basically all you're doing is you're writing down the format for Set Builder and sticking an inequality in here. And that's all there is to it. So try this out with your trim number 5. Write all real numbers greater than 7 using Set Builder. All right, start with a curly brace, variable, and vertical line. Make this line nice and big so it doesn't look like a 1. And then x is greater than 7. Now it's strictly greater because it says just greater than 7, so no greater than or equal to. So greater than 7 there, and then close it with a curly brace. Now many questions in math have answers that are ranges of numbers, not just one number. And so we're going to be writing those out with things like Set Builder notation and inequalities, and also we're going to be graphing them. So when we graph these intervals, instead of, like if we were just graphing a single number, like x equals 4, we just put a dot at 4, and we're done. But we don't have single answers with inequalities. We're going to have whole ranges of numbers. So when we do that, we're going to shade the whole range. So if we wanted to have an answer that is every number between 3 and 8, we have to have a symbol at the boundaries to signify where the set ends, and then we'll shade in the middle. And that's what a graph looks like to indicate all numbers between 3 and 8. And then to go along with the graph, there's another notation called interval notation. An interval is a range of numbers. That's what we call them. We call them intervals. And we're going to use the exact same symbols in interval notation as we use on the graph. So here we indicated the endpoints with some parentheses. So interval notation will also have the same symbols, parentheses. And then inside the parentheses, we indicate the endpoints. So we have an endpoint at 3, and put a comma, and an endpoint at 8. So this represents all numbers between 3 and 8, just like the graph. And interval notation should always match the graph. So this begs the question, are 3 and 8 actually in the solution set? Well, we have different symbols to indicate in the solution set or out. So with these symbols, 3 and 8 are not in the set because we use parentheses to indicate that the set goes right up to 3 but not at 3. So 3.000001, hey, that's in the set because it's a little bit bigger than 3. The 3 itself is not in the set. Now if we wanted to include 3, then we're going to use brackets. And when you graph these, there's no need to put in all the numbers. I don't care about those. All I care about is the endpoints. That's all that matters. And so then brackets, and they should face where we're shading. So the bracket should face inward, since we're going to shade in the middle. And shade there. Now this indicates every number between 3 and 8, including the endpoints 3 and 8. And then interval notation for this then would be 3, 8 with brackets. So 3 and 8 are in the set, 3 and 8 are not in the set. And it's a very important distinction. Make sure you understand that this means 3 and 8 are in the set, and this means 3 and 8 are not in the set. Your turn, number 6. Let's graph the inequality. -7 less than or equal to x less than or equal to 4. So we got less than or equal to, so that's a bracket. Less than or equal to corresponds with a bracket. X is in between -7 and 4, so we shade in between -7 and 4. Now we can match up inequalities with interval notation, and you can see this in the table at the bottom of the page. And I'm going to go over the ones with actual numbers in it, the -3 and the 5 ones. So there's 4 different ways that the notation can be written. First one, and we've seen this version before, -3 to 5 with 2 brackets. And that corresponds with the inequality -3 less than or equal to x less than or equal to 5. So 2 less than or equal to's, 2 brackets. And then we've got the parenthesis version, -3 and 5, and that's the same inequality, but with strictly less than. And then we can mix them up. We can have one of each. So I could have -3, 5 with a parenthesis. And then since the bracket is next to -3, that's going to be -3 less than or equal to. And then the parenthesis is next to 5, so that means on this side we're going to have strictly less than. So we can mix them up, and then the symbols correspond in order. And then we could do parenthesis -3, comma 5 bracket, and that'll be -3 strictly less than x. And then for the bracket on 5, we have a less than or equal to 5. All right, so that's the 4 ways that these can be written. So make sure you understand the association between inequality form and interval form. And then to go from interval form to the graph, we just do the same numbers and the same symbols. So that's for if we have 2 endpoints and we're shading in between. But that is not always the case. Sometimes we may have only 1 endpoint, and then in the other direction, things go on to infinity. So for infinite intervals like that, here's some examples. We may have 5 to infinity, and this corresponds with an inequality. It's not a compound inequality like these, where we've got 2 inequality symbols and numbers on each side. We'll just have 1. So this would be x greater than or equal to 5. All right, we got a bracket here, so it's greater than or equal to, and then it's every number greater than 5. So that means we go from 5 all the way to infinity to the right. Now, why does infinity have a parenthesis, whereas 5 has a bracket? Well, 5 is in the set. If we had put a bracket over here, that would mean infinity is in the set. But infinity is not an actual number, it's just kind of an idea. So we don't put it in the set. So infinity always gets a parenthesis, and that's very important. Now we could also go the other direction. What if we have x less than or equal to 5? All right, in that case, 5 is the largest number, and the larger number in interval notation always goes on the right. The smaller number always goes on the left. Now it's less than or equal to, so this gets a bracket. And then to the left, we're going all the way to the left on the number line, and that's to negative infinity. And just like with positive infinity, negative infinity gets a parenthesis. So there's a couple of options, and we could also have the two parenthesis version of both of these. So we go 5 to infinity, and that'll be x greater than, strictly greater than 5. And then we can have negative infinity to 5, and that is x less than 5. All right, so there's our 4 options for infinite intervals. So our next task is to be able to convert from one of the forms into both of the other forms. So from the graph to both interval and set builder, or from interval to graph and set builder, or from set builder to graph and interval. All right, given one, you have to be able to get the other two. So first example, we are going to graph an inequality given in set builder form. And that is x such that x is greater than 3. So the graph of this, endpoint at 3, that's the only thing you need to put on the graph is just a 3, that's our only endpoint, and x is going to be greater than 3. Now it's strictly greater, so it's a parenthesis, and it's greater, so it's to the right. So we'll color in over there. And then interval notation will be starting at 3, and it's give the same symbol here, parenthesis, same symbol as on the graph, and then we're going all the way to the right, so that's infinity. So when you indicate it on the graph, shade in and then color in the arrow to indicate we're going infinitely, and then in interval notation, it's an infinity symbol. So a shaded in arrow should correspond with the infinity symbol. And there's the other two representations for that example. Your turn, number 7. We've got x such that x is less than or equal to 6. There's our endpoint. It's less than or equal to, so that's a bracket. And less than means we're going to the left. So we're going to the left all the way to infinity, so that's negative infinity on the left in interval notation. And then a 6 on the right. And since it's less than or equal to, we got a bracket there and a bracket here. All right, now we're going to be given interval notation. We're going to write in set builder and graph. So in interval, we've got 5 to infinity. And since it's 5 to infinity, we're going all the way to the right. So on the graph, it's going to be the same deal, same direction. All right, shade and fill. And then set builder, we're going to write the inequality. So if we're starting at 5 and going to the right, that's x greater than or equal to 5. So the biggest mistake I see in these is people just getting the direction wrong or getting the inequality sign wrong. So once you write your answers, just make sure that everything corresponds with each other. We're going to the right, so it should be greater than or equal to. And that brings us to your turn, number 8. Boundary of -4, and we're going to the left, going to negative infinity, so a bracket here at -4, and shade to the left, and fill in the arrow. Now for set builder, we're starting at -4 and going less than -4, so x less than or equal to, because the bracket corresponds with less than or equal to, and -4. Next example, we're given a graph, and we're going to write interval and set builder. So the graph is out to, got a bracket at 3, and going to the left. So we have an infinite interval to the left, so that'll be negative infinity on the left, and where infinity corresponds with a filled in arrow. And then the 3 on the right, and same symbol, bracket. So negative infinity to 3. Then with set builder, x such that, and we got 3, and we're going to the left, so left is less than. So x is less than or equal to 3. Your turn, number 9. So we're starting at -3 and going all the way to the right. So that's going to be all the way out to positive infinity. All right, fill in arrow corresponds with infinity. And then we got -3 here, and since it is a parenthesis here, it's parenthesis here. And it's going to be every number greater than -3, so x strictly greater than corresponds with parenthesis, -3. Oops. Now we're going to switch over to inequalities and compound inequalities with endpoints on both sides. So the next one we're given, x such that -2 is less than x is less than 3. And so here's our 2 endpoints. So on a graph, we'll have 2 endpoints, one at -2 and one at 3. We have strictly less than, so that's parenthesis on the graph, and then shade in between. Interval notation then is exactly the same way. Same numbers, same symbols. So make sure those correspond. Your turn, number 10. So we got all numbers between -6 and -2. It's less than or equal to corresponds with a bracket. So brackets on both sides. And then interval notation is just like the graph, -6, -2, same numbers, same symbols. Our next example, we're doing -6 to 7. So on the graph, same symbols, bracket on the left, parenthesis on the right, same numbers, -6 and 7, shade in between. And then for set builder, we're going to create an inequality. So same numbers, -6. We have a bracket here, so that's less than or equal to x, and then 7 on the right, parenthesis on the right, so strictly less than. Close it off with a curly brace, and there is set builder. Your turn, number 11. All right, same symbols, going from 1 to 8, brackets and brackets, and then for the set builder, it's going to be 1, bracket means less than or equal to x, less than or equal to 8. Close off with a curly brace. Now in the next one, we're given the graph. With endpoints at -1, a parenthesis there, and an endpoint at 4, and a bracket there. So interval notation is going to look exactly the same way, -1 to 4, with parenthesis and bracket. All right, now we'll do set builder. So we're going to have a compound inequality with -1 on the left. And then parenthesis means strictly less than x, 4, oops, less than or equal to. All right, bracket means less than or equal to, and then a 4 on the end. Your turn, number 12. So here's the graph we're given. We got endpoints at -4 and 1, so interval notation look just like that. Same symbols, bracket on the left, parenthesis on the right. And then set builder, we're going to have, I don't think I have enough room. We have a compound inequality, -4, less than or equal to x, less than or equal to corresponds with the bracket, and then strictly less than with a parenthesis, and then 1. Now there are a couple special cases. With some equations, we may get no solution for the answer. And in that case, if you graph it, it's just an empty graph, no shading, and the symbol for no solution, as we saw before, is the empty set, 0 with a line through it. And sometimes we will have all real numbers as a solution. Any number we plug into an equation will work. It's rare, but it happens. In which case we're going to shade the entire graph, and then interval notation is from negative infinity to positive infinity. And that solution just means all real numbers of the solution set. So make sure you get this stuff down, because whenever we're solving inequalities, we're going to be writing our solution sets in all three of these different ways. Have a great day.